You guys, you guys can share your screen and whenever you're ready.
All right, I'll drive. Hang on a sec. Do you want me to just get going?
And we can see it. So you're ready when you.
Great. Okay. Well, thanks everybody for taking a little bit of time this morning to spend with us. I'm Bill Anderson. I'm the CTO at SecureG. I have a couple of colleagues on with me today. Todd Warble is our sales engineering lead, and Jim Payne is our VP of Biz Dev and Sales. I'm going to talk to you today about machine identity and zero trust. And hopefully, and you've heard a lot about zero trust, obviously, that's the whole point of this group. Hopefully we give you a little bit of insight into it that you haven't heard before. I'm comfortable with taking questions, going back and forth and having discussion as we go. Or you might have some questions that you want to write down and put in the chat, and we'll deal with them when we get to the end. We're going to give plenty of time for questions. We'll be out of here, I think, in less than an hour. Unless you have a ton to ask. So, but feel free to just stop and say, hey, what do you mean by that? Or could you tell me a little bit more? How would you deal with this kind of problem? We're here as much to learn from you, the audience, and sort of your experiences. SecureG is a relatively young company. We're about 3 years old. We were founded by the CTIA, which is the wireless carrier organization in the United States, and MITRE Corporation, and the two of them, and then a VC firm called Blue Ventures is also an investor in us. But MITRE and CTIA got together and said, look, there's a problem. What we're seeing is that critical infrastructure in the United States, and the specific critical infrastructure around 5G, is going to need a new kind of security approach, and something that they weren't seeing coming out of the existing players. Now, by the way, there's lots of good technology from the existing players, but there's something very specific around machine identities that we're going to talk about today. That's very relevant if you do want to try to protect the perimeter, or rather forget about protecting the perimeter and recognize that the bad guys are already in there with you. And so we were formed to address those problems. We've pulled together a very, very strong management team. You can see a little bit of people's experience. Mike, our CEO, has been at Verizon and VeriSign was one of the granddaddies of the PKI industry. I've done security, mobile security, and 2 PKI companies through my career, have a PhD in cryptography. Carlos was the CIO of the White House at one point. Jim's done every type of solution sale that there is in the telecoms industry. And we're backed up by some really, really strong folks on our board and advisors. And one guy I'll really point to, for anyone who's known anything about what IETF does, Russ Housley stands out as probably the world's preeminent public key infrastructure expert. Russ has been effectively leading the public key infrastructure standardizations for the internet for the past 20 years. And he is an advisor to us. And that, I know a bunch about PKI as well, but when it comes to the real subtleties of how do you do this correctly, what are the best practices, Russ has, forgotten more than I've ever learned about how to do these things. And he's also been exposed to the broadest possible set of circumstances in the industry. So this is simply to say, we can get you an answer to just about any question you might have about PKI. So let me talk about the reason why we're here. The industry is probably going to spend about $150 billion this year to try to secure critical infrastructure. And it really does need to be spending that money because the things that we've done in the past, what we call the legacy approach, really won't solve it. So the legacy approach has been, let's put a perimeter around it, let's authenticate servers, let's make sure that our employees are background checked, et cetera, et cetera. Those are necessary steps, but they're really not sufficient. What we need to do is to ensure that all of the little nodes, all of the big nodes, and everything in between has an identity that's built right into it, built in from inception. So built in, not added on. And you don't have to take our word for it. DISA themselves is on top of this problem. We're going to talk about some of the activity in the DOD, in fact, around zero trust today. DISA is aware that we really need to change the way we've been fundamentally thinking about securing our systems. And the easiest way for me to express it is the bad guys are already in there. They're already inside the networks. And it's not that they're malicious actors always, although there are some of those. It's that the bad guy could simply be a software process that you have running in your facility that has some extra functions in it that are insecure. Maybe it calls home to Korea, South Korea, because it's getting software updates and you didn't know that. Well, that would be a really good thing to know if you wanted to ensure that your platform wasn't leaking. The OEMs that have been developing the equipment for 5G networks are very much aware of this as well. And in fact, it was the Ericsson CTO I found saying specifically, we need to put identities into our machines. And that's what we're doing. So before I delve in a little bit more to the specifics, I was going to turn it over to Jim to talk about the evidence and the drivers about what's going on from the government side of it. So Jim, why don't you explain a little bit?
Yes, thank you, Bill. This is Jim Payne. To put the rest of the briefing in some kind of context, I think we're all hearing and reading about these directives that are coming out of OMB, White House, et cetera. And the one other thing I want to say is, in my career, I've seen the pattern where we have advisories about cloud, we have encouragement to go to cloud, and then ultimately a mandate. And that's exactly how these directives are evolving from OMB for zero trust architecture. The most recent one earlier this year was asking agencies to accelerate their ZTA plans. The most recent one announced that there will be an audit of each agency, and they give you very specific things they're looking for. One of which is to establish pilots, to be creative, to think boldly as moving, and that's a term right out of the executive order from the White House. They make big, bold gestures. The White House just released something earlier in September, moving the entire government. I just want to repeat something that Bill said. It's as if you should walk into the building each day knowing or feeling like Huawei's already there. What is your plan to mitigate that? How do you move forward? Now, some people take a shot at this by saying, well, the government doesn't really have a clear definition of what ZTA is. That's not entirely true. DOD and NSA, as DHS, have their 5 and 7 pillars. DOD added additional pillars on, and somewhere in the briefing, we're going to show you exactly where we connect to that. We also have a very important document released by CISA, NSA, and ODNI that overtly identify 13 specific 5G critical threat vectors that we're going forward. So I just want to put it in context. This is kind of the most serious thing I've seen in my career on cyber than before, and I think we have the gravity of this mission sort of central to the culture of SecureG. Okay, back to you, Bill.
Thanks, Jim. So you've heard a lot about zero trust, and probably some of you, in fact, are experts on zero trust. But for those who aren't, I wanted to sort of put this strange concept, and make it very, very simple and very real. And it really is a very simple concept. It's essentially let's do security right. We've had the tools and the knowledge to do zero trust for 25 years, at least. But we haven't really done it until now. So I think what happened was the industry really fixated on the idea of putting secure perimeters around enterprises at first, 25 years ago, to keep the bad guys out. So imagine you've got a client on the left and a server on the right and a perimeter around it. That's what this diagram shows. That was fine back then to put the perimeter around it because there were fewer bad guys. There was fewer resources to try to access. There was a lot less nodes in the networks as well. And the nodes tended to be stationary. And so perimeters were okay. But they stopped being okay a long time ago as well. And yet the industry kept selling perimeter defenses. Why? Well, because when you're making a lot of money selling firewalls, and the government is budgeting to buy firewalls because that's all you're being told, then it's really a good idea as a business to keep selling firewalls. You also tend to say that every problem can be solved with an advanced feature on your firewall. Let's just add a new feature. It's not quite a firewall anymore. It'll also do access control, and it'll start to understand traffic inside the network and so on. That's a little bit of what's going on. Vendors get really successful doing one thing, and yet the technology needs of the industry move on, and they've really moved around from this idea. They've really debunked the whole concept of having a perimeter quite some time ago. So look at our networks today. Devices come and go through the perimeter. So I have clients that go in and out of the office. So sometimes they're in, sometimes they're out. That's bad, right? Because when they're out, they might get infected and then bring it into the office. So the perimeter wasn't a really great idea, was it? And secondly, I might be accessing services, so the big orange circle to the right, outside the perimeter. I might be getting stuff from the cloud. I might be using Slack, which is running in the cloud somewhere, even though I'm inside the office, or entirely outside. And so this concept of having a perimeter doesn't even make sense when you think about how our computing devices actually interact today. And then add to that the bad guy. So here's a bad guy. They can be inside with your other assets. And you realize you really haven't had an effective perimeter. So how would a bad guy be inside with your other assets? Well, you've got Wi-Fi. Wi-Fi doesn't really respect boundaries. Well, Wi-Fi goes outside the building, which means that somebody who is outside the building could effectively be inside your perimeter. So this has not been a good idea for a long time. So what do we do about it? So that's what zero trust is really about. Is how do we make it better? We're not going to throw the baby out with the bathwater. There's a lot of good security tools out there that you will continue to use. They make a lot of sense. And one of the new ones is going to be, frankly, a lot of work to implement. Now, let me talk about why. It's really a cultural pivot when we think about how we do computing and managing our assets. It's a cultural pivot. It requires a whole bunch of new thinking, which means that your customers, your clients, whoever it is that you're trying to serve, are going to have to do some new things. And so there's a whole sort of change management process that's going to have to go along with this. This is not all about the technology, and I'll get to why. Okay, so the principles of zero trust, there's 3 of them. They're quite simple. Number 1, first you want to identify the assets that want to communicate with each other. And you don't assume that they are who they say they are. So this is best done with a PKI, a public key infrastructure, and I'll explain what that is. PKI issues what are called trustworthy identities to each asset. So they one identity for the small circle, one identity for the big circle. The assets have a private key, which they keep secret. They don't expose it to anyone else. They actually should take some certain precautions to make sure that they're always in control of their private key. And then there is, in the public key crypto system world, there's an associated public key. And the public and the private key are related. You can do things with the private key, namely signing a document that can be then verified with the public key. And by verifying, what you're doing is you're establishing that the signature must have been and could only have been done by the person who possesses the private key. That's all it is. Well, it's a lot, actually. It's a very, very cool capability, but that's all we're doing, is we're proving that we control something. And so the PKI lets these assets in the system validate identity using a signed certificate. The certificate comes from a trusted third party. So there's a PKI authority, a certificate authority that says, okay, small circle, you're Jim, and big circle, you're Todd, and I'm going to sign your public keys to say that I've tested them and I know for sure you're in possession of the private keys. So if the other party asks for a signature, which is done with a private key, you can use the certificate, which contains the public key, to check that it's correct. And if the signature is valid, then you know that the other party is who they say they are. So that's step 1. Just ask, who are you, before you do anything, and make sure the other party comes back and says, I am this person or this entity. or this virtual application, this virtual server, this IoT device, any sort of asset in your organization. Have them come back and say, I am an asset in the organization. The organization says so. You can trust me. You can trust my identity. But you can't just start communicating yet. So that's step two. The second step is you need to enforce a policy about who gets to do what, when, and with who else. Not every asset should be allowed to talk to every other asset. It's not about authentication as the second step. It's about authorization. And this is where I say we really need to see a change in thinking and some new work being done and some change management being done, because the enterprises have to start to think now carefully about what is really necessary to enable business transactions and go no further. So Todd's management server and my IoT device that controls the thermostats in the building, and Jim's security device that's used to scan the building. Those three things should be allowed to talk to each other. Maybe employees don't need to talk to that stuff. Other types of servers don't need to talk to that stuff. And so the clients who are consuming this new technology have a role in deciding what their rule sets are going to be. I'll give you a really good example because it burned the government badly many years ago. Should an Army private, have access to all of the diplomatic cables that were sent by the State Department? No, I mean, the answer is probably not. That was probably not a good call. And if someone had thought through the rules that they wanted to apply, they would have said, no, of course not. The Army private should have access to these assets and nothing else. So somebody actually has to think that through. And so the same thing goes for machine-to-machine communication. So that second step is, can I use this function? And you check at that time under those particular conditions and decide whether or not you can have access to it. And finally, you encrypt all the communication that goes back and forth between these authenticated devices. So once, by the way, you have authenticated devices, you can do the next step really easily, which is to establish a secure tunnel. This is something like, if you've heard of it, TLS, transport layer security. Other types of VPN are completely acceptable. And what they do is they make sure that all of the data between the pairwise data that's exchanged between those two entities through that tunnel is visible only to those two entities. Why is that important? Well, it actually gets back to the basic principle of zero trust. Imagine I draw a perimeter around this then and show all the other entities that are inside the facility. We should not trust any of them. And we should assume that some of them are going to try to snoop on our communications, and they are simply excluded with this model. So we now know who we're talking to. We know that we're allowed to talk to them to access this particular data or give them access to this control stream or this virtual function running at the network edge. And we've ensured that in doing that communication, nobody else can listen in. As I said, it's actually really simple, but it's incredibly powerful too, because we do this with every single communication between any two entities in the organization. There's no opportunity for the bad guys to get in anymore. Now, you need to add some other stuff on top of that, obviously, in addition to policy. One of the things to keep in mind, and this is hard in large organizations, but incredibly important, is that this system can be and really should be dynamic, because levels of trust can change, and they do change. And a good example would be, I might include in my policy decisions that I need to know that the big server on the right is actually running the latest version of a firmware patch. And if it isn't, then it may be vulnerable to certain types of brute force attack, right? So you can include in your policy decisions a measure of the health of the devices and define a threshold that says, look, this is really, really sensitive communications. I need both sides of the conversation to also be above the minimum health threshold that we consider to be important. What does health mean? It means varies by organization, but it could mean they're running good firmware, good software, they're patched, they're in the right span of IP addresses. It's the right time of day for this information to be going back and forth. And there's a lot of stuff that can go into that. And the other part about being dynamic is to recognize that the situation on the ground can change. We do our best, but devices can go bad. You can lose control of a device. It could start acting weird. When that happens, you might want to revoke trust in the device. And a public key infrastructure, like what we do and others, is used to revoke that trust. So if a device, let's say the one on the left, goes rogue and disappears for all and comes back with a very strange firmware signature, we probably don't want to let it see any secrets anymore. However, it's going rogue. You can't find it. You can't shut it down. It's on the network doing things. How do you do that? With public key, you tell everybody else in the network in a very simple way, don't trust Bob anymore. We don't trust Bob anymore. And when you do that, the very first step of this transaction chain fails. Bob says, I'm Bob. And Jim looks at the credentials and say, yeah, we're not talking to Bob anymore. Bob is out until further notice. So that in a nutshell is sort of a quick intro to zero trust. Now the DoD has been working really hard on zero trust and on zero trust guidelines. So I'm going to turn it over to Todd to talk about how machine identity principles, the sort of stuff that we're talking about here, support these DoD requirements. So Todd, I'm going to turn it over to you now and go to the next slide.
Thank you, Bill. Much appreciated. Just confirm you can hear me, Bill?
We hear you.
Perfect. So this diagram is pulled straight out of the Department of Defense Zero Trust Reference Architecture document that was put together by DISA and NSA. And what I wanted to show by displaying this particular diagram is, Bill referenced, perimeter defenses and defense and principles, and immediately went to let's deploy a firewall. When it comes to zero trust, there are a number of items that go into building out a zero trust architecture. So I think you get two things when you look at this. A, there's just a lot to be done in order to get to a zero trust architecture. We're not going to meet all of this in a Wednesday evening, 3 a.m. maintenance window. This is not something we're going to purchase a box for, deploy tomorrow, and be done. There are a lot of things to be done in order to approach the zero trust reference architecture. But the other thing I'm highlighting here with these red boxes is there's a lot of places where the PKI infrastructure that Bill was describing, a lot of places where that actually comes into play. And to be honest, we probably could highlight a couple of others in here. Not saying that PKI delivers any one of these particular things in its entirety, but that it is a foundational component for a large number of items for a zero trust reference architecture. So I want to talk a little bit about, really those drivers for taking us towards zero trust, and then also attempt to give you a roadmap. How can we actually start to deploy these things? How can we actually start to make our way towards a zero trust reference architecture? So Bill, if we can go to the next slide, if you please. So when looking at the networks of today, or even the networks of yesterday, we had an awful lot of physical network functions or physical systems that were deployed in order to be something that performed a specific function. If we needed a router, we went and bought a big router, we deployed it, we called it a day. What we're doing today as part of this entire digital transformation is we're taking all of these systems that were deployed as part of Big Iron, and we're starting to take them into more of a virtualized infrastructure. This means now I'm deploying commercial off-the-shelf hardware. I can actually deploy this stuff as needed, on demand, based on network capacity and what the requirements are at any given moment. And actually try to have best-of-breed solutions across software and hardware, and optimize my spending on those two systems. The only drawback with this particular digital transformation is that we're actually now starting to greatly expand the threat surface. So what we're seeing now are these applications, and I have a nice little diagram here of a 5G core here as an example, but really it's anything that's being deployed in microservices. We're seeing these microservices deployed over top of that COTS hardware. So now that we're starting to see a number of different things that the application itself has no control over are now being integrated into its performance. On top of that, We are deploying them side by side with other applications that may or may not have anything to do with their role in life. So, if you think about, something like the Amazon cloud or the Google cloud, or even some private clouds based on, how large a particular provider may be, you could see things like critical network infrastructure directly next to things like, HBO Max, for example. So you really have no control of what is residing on that same piece of hardware. You no longer control whether or not that hardware, has certain protection mechanisms, a la USB ports are disabled, et cetera. And then you also have these operating systems and the host OSs, if you will, where additional threats can now start to penetrate your infrastructure. So it's a highly effective means for getting these applications deployed. It's highly efficient in that it does allow you to deploy resources on demand, but it is forcing us to take a better look at everything that is being deployed so that we can secure the entire ecosystem. We believe you do this by utilizing machine identity management. Okay, Bill. We'll take a slightly deeper dive into the microservices example by looking at 5G. And sometimes the question is, why look at 5G? There's an awful lot of attention on it. This is something that DOD is spending a lot of money to look at. We do also visualize this as being part of the nation's critical infrastructure. So when we are moving more and more heavily towards 5G or wireless networks in general to be our means for access to the internet and others, this becomes something that is critical to everyday life. It's also being deployed from the ground up, from standards on. 5G is being defined as being a virtual infrastructure. So it's a very good example of that microservices use case that I was just discussing. What we're showing here is, again, that 5G packet core, and we've got some arrows here highlighting the actual communication paths that occur when a device goes to attach to the network. So the importance here is, for each one of those red arrows, I now have one microservice talking to another microservice. And this is that communication path that Bill was just discussing. And it's important to note that when you look at standards, they actually tell you, hey, you can do this a couple of different ways. You could actually just do this in the clear. Just use APIs over HTTP and you don't have to worry about it. They also give you things such as IPsec that you could utilize. And they also tell you mutually authenticated TLS is an option. In our mind, the only thing that makes the most sense, the only thing that is at all applicable specifically in a zero trust environment is mutually authenticated TLS, because this allows, as Bill was showing, you get to understand both sides of the communication path. You can receive the attestation required, authorize and authenticate the communication path, and then encrypt the data in flight. Now, the way this typically works is if you think about a single vendor deploying the entire packet core, that vendor most likely shows up with their own PKI infrastructure. So they actually allow you to say, okay, we'll just deploy certificates, as Bill was describing, for each one of these network functions. And then as that communication path goes to set up, I can establish trust between those two separate VNFs. However, if the provider starts to look for best of breed solutions, they may deploy multiple vendors in this network. And when they do that, you see the vendor B and vendor C are now introduced. Vendor B may excel in user data management, and vendor C may excel in things like radio management. If each one of those vendors shows up with their own PKI infrastructure, we are now crossing what in PKI parlance we would refer to as trust domains. So now when vendor B is talking to vendor C, if we do not have absolute rock solid proof that, if I'm vendor B, if I don't know for certain that vendor C is following all the same security protocols that I do, I can't establish a trusted relationship with vendor C. So the only real solution, an example like this, and from a PKI point of view, is to do something like a bridge certificate authority, which is an intermediary system that allows that trust, those set of trust principles to be agreed upon between the different vendors, and then the communication path can succeed. Alternatively, you could deploy a common root across the entire core. In other words, a single secured digital root of trust, which is then utilized by all the individual VNFs shown on the screen. The interesting thing with 5G is it actually allows more and more systems to deploy inside this critical infrastructure. You can see on the right-hand side, there's even applications that are being deployed by third parties directly on a very critical component of this infrastructure. So this not being a 5G specific talk, I won't go into too much about how critical the 8 or 9 boxes you're looking at are to the functioning of a 5G network. But this does show you how this comes together in a multi-services architecture, plays just as well inside of Kubernetes or VMware as it does in the 5G packet core. So how do we get started? And, by showing you that diagram from DOD, the one thing that I wanted to point out is there's a lot to be done. So I believe the saying is something along the lines of a journey of 10,000 steps starts with just one. We're going to take just one. So we're looking at the PKI installations that are out there today, and we're going to identify things that are critical to our infrastructure or critical to our day-to-day operations, such as applications that could utilize something like mutually authenticated TLS. Something that we've skipped over is that legacy PKI that Bill was discussing earlier. Quite often is server-side TLS only. So what we're going to do is actually get the applications the ability to authenticate both sides and utilize mutually authenticated TLS. We could also just as easily actually transition to what we would consider a hardened root. So this would be a common root across all of your TLS applications that would actually allow you to deploy that common set of trust principles across multiple PKI instances. The things that are happening today, the infrastructure that's actually being deployed today, specifically revolving around the digital transformation, we want to actually harden that digital transformation. We want to make certain that PKI is being implemented with a series of principles that lead towards zero trust architecture. PKI at sometimes, quite frankly, is treated as something that achieves encryption in flight. And what we want to actually do is make certain that the authentication of both ends of both parties, the authorization of that communication path, et cetera, is all integrated into the PKI services being deployed. Eventually, what we want to get into in the future infrastructure is we want to see certificates actually embedded into silicon. And what this does is at the chip level, at the moment that silicon is created at the foundry, we now have an identity associated with it, and now we can follow it through the entire digital supply chain. So we're taking baby steps today, hardening the things that rely upon PKI, giving it some better grounds to move towards that zero trust approach. We're looking at the architectures that are being deployed and making certain they're being deployed with an eye towards ZTA in the future. And then we're going to go the next step when we get into the embedded chip infrastructure so that we can actually follow this stuff from point A to point Z within our supply chain. So Bill, I think at this point, I'll be handing back to you.
Thanks. So I want to do a real simple slide from the bottom up. So if you're an engineer, you want to know where this stuff comes from, just to orient you. So the way a PKI typically works for zero trust implementation is you've got a trust anchor. So this is the private key of all private keys. It's the thing that actually on which all the trust in the system is based. So it's called a trust anchor. It sits in an incredibly secure facility. So ours sits literally under a mountain with armed guards and multiple layers of security. It then enables the certificate authority, which is something that's live. So the live CA issues certificate. So it's got its own signing key, and it's trusted because we trust the trust anchor by definition. The CA then uses a registration authority. The registration authority defines policies for who's going to get certificates. And then sitting on top of that is the system for actually provisioning those certificates. How do you get them to the device? So there's a little bit of back and forth, and it varies depending on what kind of devices you're supporting. And we support both. We support IoT devices. So imagine a memory chip that wants to be able to state where it came from. So a memory chip can have a certificate that says, I was created on this date, I have these capabilities, I was made by this manufacturer in the United States. And I'm signed by that CA, which is trusted because we trust the root. And what that means then is that the device can assert its identity in future transactions and future communications. It ends up becoming part of a larger combination of equipment. Maybe it becomes a server that's in your cloud infrastructure. And on the right, we've got cloud devices themselves. And for a cloud device for us is actually a virtual device. It's maybe a containerized application that's running on a Kubernetes cluster. Those things can have identities too. You just use slightly different ways of provisioning the identities. Once you have identities, you can actually enable zero trust systems. And we've talked a little bit about what that means. The only reason I put this up here again is just to reiterate, there's technology, which a vendor like us can deliver for you. And then there's policy, which is what the end entity actually has to decide. Who is allowed to talk to who, under what conditions. So one last slide. It won't surprise you to know, obviously, that SecureG has a solution for this. And we focus on both the physical devices and the virtual devices, and we're issuing for both. A couple of the important distinctions, particularly for critical infrastructure, is that we need to start looking ahead to quantum safe algorithms. You've heard of it. Again, I'll take just a second to explain. The public key stuff I described before, the private key and the public key, and you use the private key to sign something to prove that you hold the private key. It's been around for 20, 30 years now. But quantum computers, which are becoming feasible sometime soon, will be able to break those algorithms and make them useless for everyone in this communications strategy. And so there are new algorithms that are being standardized by NIST and should be coming fully standardized within the next year or so. We are putting those algorithms into our under the mountain root of trust, and we are going to be issuing certificates off of them. And the reason that that matters is that if you're doing anything sensitive today, you have to assume that your adversaries, while they are not able to read your communications, they can record them, and they are recording them. And what they'll do is they'll wait for a time when they can get their hands on a quantum computer that can reverse the transaction and read your mail. And so for any sort of long-term secret that you might need to keep safe over the next 20 years, you should probably start using quantum safe algorithms today in order to secure your communications. So that's what we focus on. We do a bunch of stuff in the 5G space because of our CTIA backing, and we do a bunch of stuff in the critical infrastructure space because of the MITRE, and frankly, because it is our core focus. So if someone asks you why is SecureG relevant in this space, they're a new company. There's old companies that have been doing this for a long time. I would say the answer is because we focus specifically on this space, and we are a US highly secure, we can talk about it some other time if you're interested, but highly secure root of trust. And we've built for FedRAMP certified infrastructure. So when it comes to specific projects, we will be able to run on a FedRAMP high facility. And that helps for satisfying some of the government drivers that Jim talked about earlier. So I want to say thank you for your attention so far. What I'd like to do is open up for a broader discussion now, and possibly answer some questions you might have about your particular projects. So if you want to take a minute, you could probably enter them. If it's easier, you can enter them in the chat, or you could just call it right out, and we'll do our best to answer your questions. So I guess I'll quarterback, and I'll send some out to Todd and Jim as necessary. All right, so we do have one. Yeah, so the question is, what should we be thinking about when it comes to identities for cloud systems? It's I've got kind of a long answer for that. So I think, so you got a cloud. So I think the issue is you got a cloud system, it's virtual. You can't put your hands on it. And you might have actually just enabled some new node in that cloud system 3 seconds ago. So you really have to think about, what do you know about that cloud system? Like, how much do you trust it? You probably shouldn't just issue an identity to it without thinking this through. Do you know if you are really in control of that system before you issue the identity? And I've been doing PKI a long time. It drives me crazy when I see this, but there are systems out there where the default is they just issue identities. The identities then work to enable those mutual TLS connections that I talked about earlier. But the whole thing's built on sand, because you don't actually know that you issued an identity to something that you should trust, right? So don't do that. Think about what you actually know and before you decide to issue the certificate. Next question is, are we FedRAMP certified now? No, because we actually have to have a specific project, and we don't have a specific project in a FedRAMP high facility. We designed for it, and we don't foresee any issues reaching that and run, sort of running in that facility. We didn't talk about some of the other expertise in the company, but it's based around very high security implementations. It's probably the easiest way to say. So yeah, so we actually have to have a project, but we design for FedRAMP high.
So Bill, just to add a little bit to that, the digital root, the offline root is actually stored in a facility that's designed to meet the ATO for DOD. That's another critical component of this entire path. I agree. We've designed around FedRAMP high. The facilities or the infrastructure that we've built upon is FedRAMP high, and then we are building our solution to meet the FedRAMP high recommendations as well.
We're also going through Web Trust certification, so that looks more at policies and procedures for operations, and we expect to pass that in the next couple of months, I guess, or maybe we have passed. I'm not sure. It's an ongoing process. Question from Andy Ramsey. Fed has a mature PKI. Yep. How is our capability additive or different? Fed does have a mature PKI. Lots of people do. I mean, PKI has been around a long time. The difference is most PKI was designed around having a person in the loop. And so what I mean is specifically the ones that you would know about would be ones that issue certificates to web servers. So when you're connecting with your client, you know that you're really talking to the e-commerce vendor that you think you're talking to. The other place where Fed PKI is used a lot is for issuing certificates to CAC cards and PIV and other sorts of employee identities. Well, that's a very different thing from running at a machine speed, right? When I issue to an employee, I expect them to work for me for a couple of years. I don't have to keep checking them every 24 hours. So I can afford to put the extra steps into the registration process and into the CA process that allows for sort of due diligence. And similarly with a web server, if you're issuing a cert to a web server, there's often a manual process involved in that has a human in the loop to determine, what's the Dun & Bradstreet number for this company, and do they really own the domain, and things like that. And there's been improvements in streamlining that over the last 5 years, but fundamentally, the classical PKI systems are old, and they're designed for humans in the loop. They're all based on standards, a lot of standards actually, X509 version 3 being the format of the certificate, for example. And that's great because we all speak the same language. We all speak the same language for requesting certificates and responding and dealing with various things. So our PKI does exactly the same thing as the traditional stuff. It's just that it's tuned and tweaked and designed for provisioning into those machines, whether they're virtual or an IoT device, and sort of designed around not having a human in the loop, but instead thinking about how do we do this thing quickly. So hopefully that answers the question. Any more?
This is Jim Payne speaking. One of the objectives here was not only to advance the dialogue around identity management machine, but each of your agencies are going to have to find a way of responding to the OMB mandates for audit. And what we're anxious to do is develop relationships with the agencies to show some evidence that you have a ZTA plan and something substantive around how you implement some of this newer thinking, which is one of the bold directions that the White House is suggesting. Over.
One of the questions I get asked sometimes, Jim, that you sort of reminded me is this zero trust thing, is this all or nothing? Like, do I have to go and like forklift upgrade my entire infrastructure and put in something new in order to comply or to start complying? And I would say no, generally you don't. So you can, so if you're thinking about how do I get started with this stuff, define a small pilot, define some sensitive piece of your infrastructure that you're worried about, and just do it there. You'll get a lot of benefit from simply ensuring that you know who's involved in those two sides of the transaction. Even, by the way, if you can't trust the infrastructure in between, you can still trust the communications because you've gone through the thought process of deciding, entity A is allowed to talk to entity B, and they both have certificates now, and they can talk securely. So it doesn't matter if I haven't fixed everything else in the infrastructure. I've made an improvement, a significant improvement, by just implementing it in one place. So yeah, anything is better than nothing.
A journey, not a destination.
Well, that's true too. I mean, we're never going to be finished with security. But I will say that it's nice, and I've been doing this a long time. It's nice to actually be seeing it done right, finally, with the zero trust approach. We spent a lot of years in the middle trying stuff. It didn't work. That's why security's been expanding business forever. Probably will continue to be. But we will get to the point where subverting government technology in particular is no longer so easy. And we'll be able to use the technology, and we're using technology in much broader and more productive ways because we can rely on it. And I think we're going to see over the next 5 to 10 years a real sea change where we turn the tide, and now we know that we can trust our SCADA systems, and we don't have to worry about the banking infrastructure being as vulnerable, et cetera, et cetera. One of the nice things too about this approach is it can be very granular. So there can be a large scale attack, but individual components can continue to work. And so because they're a little bit more decentralized with this system, and so they're more resilient to those sorts of attacks. The same thing goes when we talked about some security improvements that can be made around device health. So by having a thresholding scheme, for example, on what you consider to be a health policy for the day, you can survive significant attacks and keep the system operating. So to give you an example, let's say you have 100,000 drones in the field, or you're managing a smart factory, at the end of a 5G pipe, lots of devices inside the network, and an adversary decides to try to wreak havoc with you. Well, let's pretend that the attack that they use is that they have a backdoor. They've got a 0-day attack on a particular version of firmware. And then let's say that attack is somewhat successful, but your factory is not all running the same version of the firmware. Some devices are up to speed, and some devices are by a completely different manufacturer. It's only a portion of your devices that are suspect today. So with a SecureG infrastructure around certificates for those devices, you can simply exclude the ones that are suspect today, that are under attack today. So that particular make and model with that particular bad firmware, nobody else will talk to it. You don't even need to get to the factory. If the factory is a lights out factory somewhere else, you simply state that here's my security threshold, here's the health rule that's been broken. And all the other devices will know that they can't talk to those devices anymore. And so you can have a much more gradual, smooth sort of fade off in performance instead of having something that's catastrophic. So I wanted to ask then, just generally for folks who are here, did you hear anything new today? Is this approach something that rang any bells? Does it give you any ideas? And by the way, are there any sort of follow-up questions? Would anybody like to meet with us, have a little bit further discussion? Feel free to put it in the comments. But I'm just trying to get a sort of a gauge as to whether we gave you some value today, which is really the only point. Well, you know how to find us. And so we're happy to hear from you after the call. Thanks everybody for your time today, and good, thank you. Thanks for your time today, everyone, and we'll be happy to talk to you in the future.
This is Jim Payne. If you're interested, please follow us on our SecureG LinkedIn. You'll find that we're going to be posting articles almost daily about some of the developments in the Zero Trust architecture. Look forward to talking to all of you. Thank you, everyone.